the height of quasi-isogenies, which is a natural extension of the heights of isogenies. And the second point is that the formal schemes locally have ideal of definition. And well, we saw X red in Jovich's lectures. These are schemes which are reduced. Messing's theorem, by spoof of this this formal Lie variety, I meant spoof of this with that ideal, and this isomorphism is only Zariski locally. Okay. This is my running notation. I was going to explain Rapport-Zink spaces. So my aim was to explain the natural class of Rapport-Zink spaces which contain Lubin-Tate spaces. So it turns out that I didn't understand this very well. My picture is that, my height is n today because I'll be talking about GLN rather than, it was h yesterday. Maybe I'll use the other board. And B is this Newton polygon, and the Hodge polygon would be n minus D. This is mu or minus mu if I use Segu's notation. So I want n and D to be co-prime just to make sure that the endomorphism ring is the order of division algebra. This is unique up to isogeny. So I think this this will make the reflex field equal to K. Well, I'm not entirely sure. This will be true when D equals 1 from the next section. So assuming this is true, so this will be my base ring, maximal ideal P, O unramified hat, this is the maximal unramified extension. So P O hat, residue field K bar. I'll use the notation O nilp for the O hat algebras in which P is nilpotent, so that a spiff of O hat sends R to a singleton or empty set according to whether R is in O nilp or not. So Rapport sync space is defined as a moduli functor on O hat algebras. This will only have values if P is nilpotent, and if P is nilpotent in R, then I can comfortably talk about Barsotti-Tate modules over R. So, sorry, this is curly G. So G so R over P is K bar algebra. So I'll tensor up, and then this is a quasi-isogeny of sigma 2 G. Okay. So what Rapport sync proved is that M is a formal scheme over that spiff. Disaster is that I left this book in England. I couldn't look up the definitions. So this is a special case of a more general definition. What you see in many of the literature is the unramified case where O is unramified over QP. That will make things easier. Or it can have more additional structures, like it can have actions by semi-simple QP algebra, or it can have polarization and so forth. I'm not going to go into general properties too much. The existence of the height of quasi-isogeny, that's always an integer, and the fact that this is constant over connected rings means that this will be disjoint union of locus where the height of rho is h. J is an usual notation for the group of quasi-isogenies. So this is a group. And in this case, J equals D cross D over K is division algebra of and this will naturally act on my space. Because you can compose your quasi-isogeny on the domain of rho. Okay? So it's going to shift the height of rho by the height of delta. And because the quasi-isogenies are invertible, this is going to be an isomorphism. All right. So what are these division algebras? It has a ramified extension of degree n inside D, and it's generated by pi. This is this is a prime element of D, and which whose nth power will be a uniformizer in K. So let's denote by VD the normalized valuation on D. Then looks like this, and OD is the maximal order. So So the division algebra having invariant D over n means that you can find an element f of valuation D such that it normalizes L but conjugation will give you the Frobenius of L over K. So that's this is from the theory of division algebras. Okay, and so now back to our Barsotti-Tate modules. So J is the D cross, and I can choose sigma over K, the residue field, so that this is actually sigma. So this is the relative qth power for Frobenius. I mean, if this is not so important. If I choose sigma over K, then I have canonically isomorphic. If not, then I can choose an isomorphism. And VD is the height of the quasi-isogeny. So the height of the uniformizer small pi was n, and that's compatible with that. Okay. And D, I said that it was the dimension was the height of the relative Frobenius. And that's compatible with what we saw above, right? So here's something that I don't understand very well. I have D and OD, and I have N sigma in it, and so you can compute this endomorphism ring using the Dieudonné theory. And I think this is equal to OL F if D is smaller than N minus D, but not entirely sure. Okay. And D cross has OD cross in it. So that was the kernel of BD, and that's a group of quasi-isogenies of height 0. And inside, I have end sigma cross, which is the automorphism group of sigma. Okay. Above, yes. That the normalizer of L cross maps surjectively to the Galois group, or something like that. If I take the normalizer of L cross inside D cross, then this will be Gal L over K. And that will give you the extension of the Galois group by L cross, and that corresponds to the class in H2 of Gal L cross. And that's where the invariant lives, and things like that. Okay. Right, but in our case, we know that we have a nice element F coming from geometry, and this relation is kind of obvious if you think of what this relative qth power Frobenius is doing. So it all fits in nicely. So the great fact about d equals 1 is that these are equal. And in general, this is not. So I learned from Miyada-kun that, for example, you can think of elements like this. I mean, this works only if my conjecture is true. But it's certainly true that these are not equal in general. Okay, so this makes the case d equals 1 very simple. So we'll see how. When d equals 1, the Rapport-Zink space is called the Lubin case space, and this came first. And the consequence of the fact above is that the reduced scheme of M0 is the part where the quasi-isogeny has height 0, is a point. Okay, so this is in general a scheme over K bar, which is spf O hat red. Sorry, spec K bar. But this has to be one point, and that follows from that fact. Well, K bar is a field, so it's reduced. K bar points all factor through the reduced part. And what does this classify? It's a pair of G over K bar and rho up to isomorphism. Now fact implies over k bar, quasi-isogeny of height 0 is the same thing as the isomorphism. This set being an automorphism group torsor, and this set being OD cross torsor, and these are equal. So there's only one point over k bar. In a reduced scheme, has to be the spec k bar if it has only one k bar rational point. So once we have this, M0 is both of AI, where A over I, M red is k bar. Okay. So I mean, if you only care about the reduced part, this is just one point, and this space is not so interesting. But the whole complexity of this space lies in the nilpotent part. But that will also turn out to be quite easy to analyze. Sorry?
In this case, A may be equal to hat.
O hat.
Is that the case?
That's a good guess. When n is 1, you're right. All right, so this is formally a finite presentation. I think this is a this comes from the fact that the moduli functor is defined by a finite amount of data. Now, M0 is determined by its restriction to the subcategory of Artinian local algebras. Whose residue field is just k bar. Okay. Okay. I mean, this is saying that so our rational point for arbitrary R will actually come from a rational point over some ring whose reduced part is k bar. Okay. Each of these A over IM is a ring with a large nilpotent, potentially large nilpotent part, but only one point, right? So such a ring is always a filtered direct limit of Artinian local rings, and so those will control all the rational points over all the rings in O hat algebra. Okay, so So let's look at what this functor is doing over C, this smaller category. Am I going in the wrong direction? I did that. Is this okay? I think it's... Somehow the English students are insisting that I should go horizontally in terms of blackboards rather than vertically because I go too fast or something. I'm trying to practice here. So, what are these G and rho? So G is over R, this Artinian local ring. Now rho is a quasi-isogeny from this to this. But now we're looking at M0, so this is quasi-isogenies of height 0. Okay? So I remarked over here that over K bar, quasi-isogenies and isomorphisms are the same thing. Now, this ring, R, has, this is a non-reduced K bar algebra, which means that this may not be isomorphism. But there's a theorem called Riemann-Feld's rigidity theorem. So suppose I have a ring in which P is nilpotent, okay, and I is a nilpotent ideal. So for example, in this case, R is Artinian local ring, and P is an nilpotent ideal. Okay? And P is nilpotent, of course, and also the maximal ideal M is nilpotent, okay? Because R is Artinian. Then a natural map from the quasi-isogenies to quasi-isogenies over R over I. Just pulling back to R over I, this is bijective. So this entails the following fact. So if I have an Artinian local ring, then okay, what I had is a quasi-isogeny of height 0. And this was hard to control because they may not be isomorphisms. But I can pull it back to the residue field. So use rigidity for I over n, I equals n. Then I get back sigma over K bar. And this is going to be what I see over k bar. And if I pull back my quasi-isogeny, then it's still height 0. And this is over k bar. We know that these are all isomorphisms. Okay? We did that before, above. Okay? So in other words, any isomorphism over k bar between Bar-Salty-Tate groups of dimension 1 will lift uniquely to Artinian local ring of characteristics P, uniquely lift to quasi-isogeny of height 0 over such rings. This takes us to the classical definition of Lubin Tate space. So that's the usual kind of deformation functor. So this is a functor on C, which I call def sigma. But now my rho is an isomorphism over k bar. And R is the Artinian local ring. So this can be analyzed by the usual techniques of deformation functors. This is formally smooth, which means that it's always liftable when you have a surjection. Now, when it's formally smooth, you only need to look at what it does on the dual numbers, the ring of dual numbers, which is also called the tangent space of the deformation functor. Now, this turns out to be k bar to the n minus 1. So when n is 1, the tangent space is 0 dimensional, and you do get O hat, but in general you don't. This implies that what you get is this formal power series ring, and the ideal is the maximal ideal. Well, once we know what M0 is, if I choose a pi, then as I remarked some time before, it will give you an isomorphism between the height 0 part and height I part. Hence, you have the distant union of these spf A's indexed by Z. So of course the 2 is a non-trivial part. This is proven by, you have to do some work. The original proof was by working with formal groups. Or you can do crystalline Dieudonné theory. So according to the theory of Dieudonné crystals, deforming my Wasatchi-Tate group corresponds to deforming the filtration on the Dieudonné modulo P, the Hodge filtration. Dieudonné modulo P is like the de Rham cohomology, so it has Hodge filtration. It has rank n, and the quotient is equal to the Lie algebra, the dimension. So it has codimension 1, so I have n minus 1 dimensional space, and I want to deform this to that ring of dual numbers. And because this is n minus, it's like Pn minus 1, I get n minus 1 of freedom of choice. Any question? I was going to just explain how rigidity theorem easily implies Serre-Tate, which I stated yesterday, but perhaps I should move on. Yeah.
That you were creating with no computer expression.
Oops.
Yeah. Because you get the A bar rational quantity, like a single point equation paper, but it's not true.
Or finite type.
We know that M0 is homogeneous to finite type of
Thank you. Yes, yes. I think I was writing this at around locally a finite type. Yes. sorry, yeah, I was using the finiteness over here, sorry. It was like 5 in the morning when I was writing this. So I think we're going to hear more about Rapport zinc spaces in the following talks. So I'll briefly go through what level structures mean. So lambda is the rank n O module. V is the rank n vector space over K. G is the GLN of K. And U, 0, is the automorphism group of lambda. So I consider lambda as contained in V. This is GLN of O. And we learned from Miura-kun that we can associate a rigid space to a formal scheme. This is n-1 dimensional open polydisk. Of radius 1. Okay. And now what is G on M-rig? G is now an atoll sheaf. I mean, it was an FBPF sheaf, but now it becomes atoll sheaf because we're in characteristic 0. With stalk isomorphic to B mod lambda. This is K over O to the n. This is like QP mod CP for any geometric point. Do you write rig as a subscript or superscript? Is this okay? And note as an O module, I can take the automorphism group, and that's again U0. Sorry, did I U0? Yes. So for any open compact subgroup, so this is going to have finite index because U0 is compact. This is a relative moduli space. I mean, I'll use the same way of defining this as in the Shimura variety case, but I'll explain what it means later. So I had this isomorphism eta, but here I have U0 acting on it, so I have U acting on it from the right. So I can take the orbit. So I have to choose x in mi for each I, but these choices are irrelevant. Optocanonical isomorphisms. And more concretely, if for each integer m, if I have the principal congruent subgroup, this normal subgroup of U0, then level UM structure means you're giving an isomorphism between this constant module and the p to the m torsion points. I'll just go on for a few more lines. Then I think in this case this is automatic, but in general it's not, right? So that's going to be GLN of O over PM covering. Of M rig. So smaller u means higher level. So you can go from higher level to lower level. And I can define a map G so for each G, U has to be small enough so that these are defined, but where I have a tower of rigid spaces which have action of G and J which commute with each other. J is the one I defined before. So the action of G is called the Hecke correspondence. A few remark is that so it's elliptic atal cohomology, which is another name for nearby cycles at M red, which was a point. This is because these formal schemes are just strict local rings. So the atal cohomology of the generic fiber is the same as the nearby cycles at the closed point. So these realizes yeah, but they're just Z points. Thanks. This was shown by Harris-Taylor, and they're complemented by Boyer and Dat. This was also shown by Harris and Taylor. Nowadays, it's proved locally by Straw and Mieda. These are local, but everything else is global. Another remark is that MUM rig, these special principal congruent subgroups, UM, has regular formal models. And that is an important input for all of these, these works of Harris and Taylor. All right, that's it for the morning.